Hello, good afternoon, everyone. I'm very pleased to welcome you for this online technology meeting on photonics for cultural heritage. I'm Jérémy Picot-Clément. I'm technology manager at EPIC. And before to start, I would like just to very shortly introduce you to EPIC. So EPIC is the largest industrial network in the world in the field of photonics. We have now more than 800 members. We cover all the photonic value chain, from the photonics industry, photonics component manufacturer, design and prototyping company, and we include also end users and system integrators among our members. We cover also all the photonics application, which is quite wide. So we include, of course, cultural heritage topics, but also, space, defense, biomedical, quantum, augmented reality, agriculture, etc. Everywhere where we can find photonics, we are covering it. And our aim is, to create a sustainable European photonics industry. And how we do this, we organize, like this technology, online technology meeting, but also physical meeting. We provide technology support to our members. We have also market and technology reports I would say every 2 months, accessible to our members. We provide also some networking opportunities, access to market. If you want to go to Asia, if you want to go to the North America or South America, we can also support you. Mentorship, HR support with the website Jobs in Photonics, and also investments. We have a list of investors, which are interested in investing in photonics industry. Here is the team, the EPIC team. So we're 11 people. I'm a part of the technology team with my colleague Antonio Castello and Ivan Nikitsky. Antonio is more for biomedical and laser topics. Ivan will be more on quantum integrated photonics, and I will be taking care of imaging system, optics and optical systems as well. We have also a team dedicated to marketing, a team dedicated to logistic, and this is how we work. A very short overview of the next event we'll organize. So as I told you, we organize in-person meeting and also online meeting. But in-person event will be at Singapore for APE, will be in Netherlands for something on PIX, also something on defense in France. We'll organize the AGM in south of France in April, which is our biggest networking event, and then we'll be also in Germany, sorry, for an event on space topics. And then we have also online event, not talking only about technology. We talk also about marketing, recruitment, also sustainability for photonics industry. So it's quite wide. Here is all the companies that register for the event today. So as I said, we cover all the photonics value chain. We have end user and system integrators, software and design company, material company, and of course, research and development institutes. We have also several component and modules companies, equipment manufacturer, of course, and other kind of companies. Here is the agenda of the today's event. So we'll have 7 talks. We'll start with you, Marie-Ève Didier, CEO and founder at Matisse. We'll continue with Nireos, Marta Girardello, then Spectalion EAS, John. We'll welcome you for this talk. Then we'll continue with Sinova, Nitin Shankar, Clyde HSI with John Gilchrist, and Hyrox, Emilien Leonard. And we'll finish this meeting with Xpectral Tech with Ali Kamalabadi. So thank you very much for being here. We'll take a few minutes after each presentation for question and answer. So feel free to raise your hand through Zoom and ask any question you will have during the meeting. And thank you again for your participation. And now I will give the floor to the first speaker of this afternoon, Marie-Ève Didier, CEO and founder at Matisse. So thank you, Marie-Ève. And please, the floor is yours. You can start your presentation.
Very good. Thank you very much for this introduction. And since I've done before, now I can share my presentation. Here we go. right. Good?
Yeah, perfect.
All right, perfect. All right, so Matisse is a startup based in Switzerland, in Lausanne. We are on the market since a year, and so I'm going to talk about like the new development we've done with multispectral imaging. Of course, you know all about that, so no need to go very much into details. So it's just to show you a little bit of the evolvement because of course, restricted vision, RGB, it's our eyes. We see limited things and we can then decode the limited things. Then the limited vision, so with standard cameras, have a bigger sensor and of course with a different sensitivity of a different spectral range. And multispectral enhanced vision that we call because it's using still a sensor like a CMOS sensor, and it is enhanced because not only we have a longer, bigger range of sensor, but also different illumination. So what we do at Matisse is illumination-induced multispectral imaging technology. It consists of three things: the camera, the software, and the analytics with machine learning that we develop ourselves with physics-informed machine learning neural network. How it is, Matisse illumination-induced multispectral imaging system is super easy. You take it, you click, you have all the spectral, and then you go onto your computer. So why this? Because we wanted to have a portable, very easy to use system. We all work in cultural heritage. We know how difficult it is sometimes to access, in the tomb of the Ramses III or in Luxor or some other areas where we cannot put a tripod, we cannot put a lot of lights around. So that's why we wanted to have something as an immediate diagnosis tool that brings the lab to the artworks and not the other way around. The software, extremely important as well, because what do we show? So how do we show it? What do we show? Is it validated by the technology and also by by the stakeholders? And we call it Art's digital fingerprint, because with this imaging system, the camera and the software, we can extract meaningful information. So what is this thing? So compared to, for example, that's what I was telling you first, we focus on the usability and portability. Between the traditional MSI and the Matisse multispectral, this is a reduction of cumbersome equipment. Our system is only in one luggage. You can carry it through all the weird borders we tried, believe me, and it works very well and it's very portable. You saw how it works. What do we see? So we wanted to see something from the surface of the artwork to in depth. Of course, there is restriction. As I told you, we have a CMOS sensor. And we want to use all these single wavelengths that reveal the DNA of the material. So how do we go through intensity? Because I didn't talk about putting a target for calibration and stuff like that, to reflectance, what we call material DNA. Very easy. So our camera is a data generator. And we do the transition between the physical material, so it can be on artifacts, cultural heritage artifacts, or raw material like pigments, binding media, varnishes. And all these things, we give results and diagnosis with the AI-driven algorithm. One shot, first of all, we have one shot 15 images from UV to IR. And each of these LEDs or these bands are illumination induced. First of all, we carefully chose these LEDs based on machine learning algorithm from a database of about 300 historical spectra. And we ask the algorithm, tell me where to put the windows, the spectral bands, so that we have a better diagnosis on identification of those spectra, of those pigments. That's how we came up with our set of 15 LEDs. And so we generate a lot of data with those one click, 15 images. However, we need to have good data. So we incorporate into our camera what we call the interesting calibration. So once you take an image with your camera outside, then you upload it on the software. When the upload is done on the software, the camera is white balance, calibrated, flat fielded, and normalized. And this allows us to do two things. One, the extraction of material DNA, let's say reflectance spectra for identification, and also the monitoring. Monitoring because you can take a picture here at one time, and then the same artwork in an auction house, for example, in 3 weeks, then you will be able to compare them because they will be calibrated and normalized. So we wanted to develop a system that is easy enough that anyone that is not an engineer nor conservation scientist can use it. For example, there are a lot of art historians, restorers, people in a laboratory, for example. Not everyone is a chemist or like a physicist or image processing or computer vision specialist. So that's why we wanted to help those people to focus on interpreting the data and not using registration and all these things that are extremely cumbersome. So how do we use? I'll go fast on this few examples. We have a training data set. We use convolutional neural network, pixel-wise, to generate masks and give results. And this is extremely easy. So that's, for example, you all know about the pigment checker here from Cosentino. And that's a very easy example. So you can see that we run our algorithm. We can do mapping, it maps, and identification, of course, with each of them. How about in real life? In real life, for example, it can help for a diagnosis to identify the restoration processes. Here, it's on the Japanese print of the 19th century, and you can see that the restorers, they wanted to know if the background has been retouched or something like that. It was super, super fragile, and they couldn't do sampling. So we did like one click, we run the algorithm, and we find out that actually the background and the flower are not the same. So then it helped them understanding the material that give them an idea on how to do the restoration processes. But it can also use, for example, as I told you, to map, for example, to be able to see where is, for example, this tallow green, and that is also to understand for authentication or something like that, it can be used. And what I wanted to tell you, it's, of course, when we do pigment analysis, everyone will ask, yes, but there is mockup and real life. So mockup, very good. We know which spectra is one. For example, this is a model that we do for Egyptian pigments. We have a running project on the King's Valley. And this is on stone in the tomb of Ramses III. Of course, you can see that the spectra are different. But that's why it's important to have a good amount of data and a variety of data. So that's why our team is actually doing real data, simulation, understanding the essence of the theory of light and matter, absorption, reabsorption, and emission, so that we can combine those things together to give a good diagnosis. And in this case, we can give not only a diagnosis, but also what we call a confidence map. Because the confidence map is not also the results of the machine learning, for example, is not only here to give you just a black and white diagnosis, but it has to be taken with the grain of salt. So that's why the confidence map is extremely important to integrate into the software when we give the diagnosis, for example, so that the human stays at the center of the decision and the diagnosis. So that's in a nutshell. I know I have 10 minutes, so I will just leave the floor open for like a lot of questions, I hope. And in a nutshell, that's exactly what we do at Matisse. So for example, we have the data generator, the camera that we developed, the algorithm we developed, and then after the goal is to produce this kind of map with classification, identification, and diagnosis for the art ecosystem. So voilà. Thank you.
Thank you, Marie-Ève. Any question for Marie-Ève? You can raise your hand through Zoom, the bottom. Yes, please, Joe.
Thank you. Thank you very much. Very, very interesting presentation. I look forward to learning more about this. This is a very interesting topic that we have been working on also. I had a question, just particularly you were mentioning flat fielding, and I was wondering how you're doing that, because I mean, you know the light distribution, so but do you still kind of use some kind of uniform
Yes.
surface to do the flat
Of
fielding?
course.
Yeah,
Yeah, very, very good. Yes, yes, we do. That's how we extract reflectance, so that pixel-wise we don't have like intensity, but really a reflectance that has data that has chemometric analysis on that. So yes, we have a huge white reference on which we of course we do different acquisition, and then after we do extrapolation on the distribution of light and stuff, different parameters, because on a camera like that you have like a lot of different parameters. You have the ISO, you have the acquisition time, you have the focus, you have different things. So we run simulation so that we have this in between the one that we take, and then we have this database of right reference which we use for when the images are there.
Okay.
Thank you, Joe. Any other question? Yes, please, Konstantinos.
So out of curiosity, I see that, in the device, the camera is used Canon. So can this anything be retrofitted to other cameras as well?
Yeah, we chose Canon for different reasons, but it can be also fitting on other device. It's not a problem. And then there is of course a small adjustment of the training set. However, nothing's changed in the process. It's okay.
One more question. So one of your, let's say, standard picture analysis, how much memory it takes, how many gigabytes you generate per painting?
Yeah, good idea. So I know that my CTO is watching me and he will help me. It will, I don't know. I don't know. I can tell you that after, but it's not much. But that's a good question. I can tell you after. I don't want to say like bad stuff unless he's sending me a team meeting, a team message now. I can answer, but we'll see.
Okay, I think we can talk after the
One
meeting.
giga. 1 giga.
1 gigabyte. Okay, got it.
Thank you, Sebastian.
Yes, John. Go ahead.
Yeah, you have to watch the time, so we can keep talking on this. I was thinking about specular reflections and stuff like that, because you have a fixed, light in geometry and it's pretty close. So depending on the properties of the objects, you might have that. Is that something you treat in post-processing or try to avoid, or do you do polarizing, or what?
So we use that. So my background is physics, so I have my PhD in physics. So we use all the tricks we were using in the very like nerdy stuff. So of course we integrated like polarization, right, and different style of different polarizer. So we don't have any specular reflection. Yeah. So it can go on glass, and the artworks be behind a glass porcelain, very highly reflective varnish. Anything works, and it doesn't affect then the reflectance also.
Thank you.
Yeah.
Yes, okay, thank you. Yeah, we have a question. Oh, no, it's Sebastian. Okay,
Yeah.
he answers the question.
Perfect. See.
Perfect. Thank you,
Good
Sebastian.
team.
Okay, so thank you very much for the question,
Welcome.
guys, and thank you again, Marie,
You're
for
welcome.
the presentation. Thanks a lot.
Bye.
So we can welcome now our next speaker. Welcome Marta Piardello from Nigeos. And Marta, you are technical sales manager. So please, the floor is yours, Marta.
Thank you, Jeremy. Let me see if I'm able to share the screen correctly. Voila. Okay, can you see my screen?
Yes, you can start.
Okay, good. Thank you very much. So good afternoon, everyone. I'm Marta Girardello, Technical Sales Engineer at Nigeos, and today I would like to present you our hyperspectral camera HERA and its application in the cultural heritage field. So recently, there has been an increased interest in hyperspectral imaging applied to cultural heritage, highlighted not only by the increasing number of publications, but also by the fact that there are several European projects and infrastructures built to transform hyperspectral imaging from a laboratory tool to a standard resource for museum and archaeological sites. Why? Because hyperspectral imaging is used for pigment identification and mapping to reveal hidden details of your painting, of your art object, but also for condition monitoring and conservation. All this information helps conservators and restorers in the restoration or authentication process of the artwork. There are on the market several methodologies to perform hyperspectral imaging, such as snapshot imaging that use filters in front of the camera pixel, or staring imaging that use filter in front of the entire sensor to record the spectral information, but also push broom systems that use essentially two-dimensional detectors, and they scan line scan the information to record the spectrum and the spatial information. Our approach is completely different and is based on Fourier transform. If you have in mind Fourier transform, essentially you create two replicas of your light, you delete the replica of a certain time t, and then you let the light replica interfere. In this way you obtain an interferogram, and then of course by applying Fourier transform you retrieve the spectrum. Of course, it's very easy to do. You have all in mind the FTIR devices in your lab. And it's very easy to do when you have a single pixel detector. But then when you want to go to imaging and also to a portable system, it can be quite tricky. And in principle, you can do that. So you just need to record two images, delay them for a certain tempi, obtain a time domain data cube, and then apply Fourier transform. Of course, you have to satisfy some requirements that are not very easy to satisfy. I will not go into the detail, but I just show you our solution. Here you can see a sketch of our common path birefringent interferometer. Essentially is an interferometer based on birefringence. So instead of splitting the light in different optical paths, you split the light in polarization. This kind of approach has huge advantages because it allows you to achieve a very high stability and reproducibility between the light replica, and achieve a very high accuracy in the delay. Indeed, you can work with Fourier transform not only in the infrared range, but also in the visible one. The interferometer is also very compact because it's 3 centimeters wide and it's ultra broadband. These last two properties have a huge impact for us because essentially we were able to, let's say, bring the technology built in laboratory to a commercial device that you see here, that is our Hera hyperspectral camera. But also since the interferometer is ultra broadband, we were able to develop different models accordingly to the sensor that we choose for a total range of coverage from 400 nanometer up to 2200 nanometer. So what are the advantages of Fourier transform and why we do use Fourier transform for cultural heritage? Well, first of all, Fourier transform have this huge advantage of having a very high light throughput. So you are not using gratings or filters, so you collect all the lights simultaneously, and you can work with low light illumination condition and also with diffuse light illumination. This is extremely important when dealing with cultural heritage object, of course, because this allows you to reduce the light dose that you give to your artworks. The second very important characteristic of our camera is that it has a spatial and spectral resolution that are completely independent. You can increase the spectral resolution via software without compromising the throughput, and the spatial resolution is not related to the sensor that you choose and the distance at which you do your measurements. Then the technique is stationary and non-contact. So you can point and shoot your camera through your object and record your hyperspectral data cube. And you can work also at smaller distances like 25 centimeters to record some details, and we will see after how we do that. Also, you can mount it on a microscope, and we will see it later how we can do that. And Finally, it's very portable and lightweight as a solution, so you do not need movimentation states, so you can use it also for in situ measurements. So now I will show you some example of the different kind of measurements that I mentioned before. So let's start with the remote or wide field imaging. Here you can see our Hera in action in Santuario di Saronno on a Bernardino Luini painting. So here you can see the reconstructed RGB appearance of the wall painting based on the reflectance data. And as you can see, we concentrate our attention on the blues used by Bernardino Luini. You can see from here, from the, let me just use my pointer, okay, here, that basically the artist used two kinds of blue. One is lapis lazuli that has a high reflectance in the infrared, and the other one is a smalt-based mixture that has two inflection points in the visible range. On the basis of this reflectance data, we were able also to obtain a classified image where we're also able to extract some information related to the painting technique. Indeed, you can see that for the vest of Mary, he used only lapis lazuli, the most precious pigment, while for the vest of Joseph, he decided to use a smalt-based mixture pigment and lapis lazuli to obtain the shadowing effect. As I was mentioning, the camera is quite flexible and you can use it for also macro imaging. Indeed, you just need to add a lens in front of the threaded aperture of the camera. You reduce the working distance and you can do some measurements of details of your art object. This is quite fundamental when you're working with non-flat object or non-perfectly flat object, like, for example, illuminated manuscript, because you cannot measure them in microscopy because otherwise they are too rough. You want to have a very high spatial resolution, and maybe you are not in the best configuration when you do wide field imaging. So by using this macro configuration, you are essentially keep the compactness of the device, and you are able also to do some more detailed imaging. If I just tell you this story about this illuminated manuscript, so essentially the conservator and restorer performed the X-ray fluorescence mapping that you can see here, and you can see the distribution of lead in this map. And as you can see, there are both pink and red pigment that corresponds to lead white, or lead-based pigment better, because the map refers to lead. If we go to X-ray diffraction, we can see that basically the pink region corresponds to hydrocerussite that instead is a white pigment, while the red region corresponds to minium that is a red pigment. So the question from the conservator and restorer was hydrocerussite mixed with minium, or was mixed with a different kind of red pigment such as lake pigment that are not visible to X-ray fluorescence and X-ray diffraction? Well, we performed reflectance measurement on a portion of this illuminated manuscript, and it's not very evident from the reflection data set, but it's quite evident in the first derivative that there is that peak that can be attributed to a red lake mixed with lead white pigment. The last configuration that I would like to present you is microimaging. In this case, you can see our Hera mounted directly on the C-mount port of the microscope. And it's very easy, very straightforward. You just mount the camera on the instead of your usual camera that you have on your microscope, and you record your measurement. In this case, we have recorded not only reflectance measurements of our paint cross-section, but also UV excited and blue excited photoluminescence measurements. And then we have done a combination of the data set by fusion of data sets of reflectance and photoluminescence data set, and then applying some spectral unmixing and classification. I just give you a little bit of quick introduction of this, but the results are amazing because you can see you can classify very well your paint cross-section and identify some pigments like cadmium yellow, cadmium orange, chrome yellow, and other kind of pigment present in your paint cross-section, completely non-invasive and using only the optical, let's say, information that you have. With this, I hope that I give you a glimpse of our Fourier transform-based hyperspectral camera. It's a very unique device, portable, compact, but also very flexible, because with one device you can do different kind of measurements. And I think that I am running out of time, so if you have any question, please feel free to ask them.
Thank you very much, Marta, for your presentation. Okay, we have time for one question for Marta. If you have, yes, John, please.
I can always ask a question. I was wondering about the resolution, because I was intrigued. You said the spatial and the spectral resolution, they are independent, etc. But do you have some numbers, or what kind of resolutions are we talking about here? What spatially and spectrally?
Yeah, sure. Well, in terms of spatial resolution, for example, the visible near-infrared camera is 1.3 megapixel. So at 1 meter distance, you have roughly 110 micron as a pixel pitch. And in terms of spectral resolution, you can be as good as 1.5 nanometer at 400 nanometer and roughly 9 nanometer at 1000 nanometer. Then, of course, these values vary accordingly to the distance that you use, and of course to the scan length that you use for the interferometric scan. Of course, the longer the scan, the higher the spectral resolution.
Mm-hmm. So there's a trade-off with time. You say the
Absolutely.
longer scan, yeah, you scan for a longer time, and then you get the higher resolution.
Exactly. Yes.
Thanks, John. Yes, Konstantinas, please.
I have a very short question. So you mentioned that in your spectral camera you're using a this birefringent prisms. So this is similar to differential interference contrast microscopy, or can you elaborate a bit more how it works?
Well, I don't know if we have time, but otherwise I can share with you our published paper later. Essentially, we use birefringent wedges. Okay, you have as a first element a polarizer. Then you have these wedges that moves. One wedge moves on the hypotenuse of the other wedge. And essentially, this allows you to change the thickness of the birefringent material. By changing the thickness of the birefringent material, you change the delay between the light replica, and in this way, you obtain the interference. I have a nice paper of that if you want.
I will. I will ask you for it.
Good. Thank you. Thank you very much.
Thank you, Marta. Thank you again for your nice presentation, Marta.
Thank you.
Thank you. So now we can move to our next speaker. Welcome Spectralion AS with John Hardeberg. So please, John, you can start your presentation.
Yes, I will try, and I will try to share. And it's unfortunately a bit widescreen for you, but that was the only thing I could figure out how to see it. I hope you can. Do you see my slides now?
Yeah, it's okay.
Good. Thank you very much for inviting me here. Meeting new people, discussing already, having heard two very, very interesting presentations. I would love to talk more to both of you. I represent, I would say, first, most of my time goes to NTNU University. I'm a professor at the Norwegian University of Science and Technology in Gjøvik, Norway, at the Color Lab there. But I also have this spin-off called Spectralion. So I kind of have those two hats, so to say, on me today. Talking about spectral imaging for conservation science in general, quite, so some examples and some things I bring to the table there. We don't make devices really. We might put together some things in the lab, but we're not kind of in the industry of making devices. But you can see we are using devices, and we are doing a lot on the analysis and use side, and kind of let's say between the camera and the user in the field of conservation science. Well, I don't have to argue. Well, depending on the audience, you have to argue for spectral imaging in different ways. And here is a slide I use when I come from color, because color imaging is kind of a known thing, and people understand that. And sometimes color is not enough. What does that mean? You have to go, what are the limitations of color? Why is color? Why is it not enough to have a color image necessarily of your, cultural heritage object? So I don't think I need to necessarily spend time on arguing for that, but in some cases that's important. There's metamerism, for instance. Different spectra have the same color, so that's one of the things that can be illustrated. So yes, sure, we focus a lot on the spectral reflectance. That's kind of what we're trying to measure in these images, and maybe mostly in the visible light, or even starting from there, but of course going into the ultraviolet, going into the near infrared, or even further depending on the application. But sometimes you have to kind of argue that even without going out of the spectral of the visible range, you still color is not enough. 3 numbers are not enough. You need the spectral reflectance even within the visible range, right? So there's a lot of words, concepts being used, multispectral, hyperspectral. What is the difference between that, etc. We sometimes I just want to talk about spectral imaging. Well, there's a pretty broad range of different technologies, different definitions and usages that falls into this field. So it's a pretty big field. Not only for cultural heritage, conservation science, but also for many other applications, obviously. Now, multispectral imaging, well, this is probably too basic for you guys, but this is kind of just one of the ways to capture multispectral images, right? You have a 2D sensor, and then you take several images through different filters. So you get the multi-channel, multispectral image, and then you have the scanning approach. And here are some examples of that. There happen to be 2 cameras here. I will get back to that. But so I mean, many different ways to doing it, with their different trade-offs and qualities in general. Now, why is this relevant for conservation science? I here kind of just group in 3 things you might think of. One is kind of, let's say, the documentation of cultural heritage objects in different ways. When people say documentation, many think about just taking photos of the objects or of the conservation, restoration processes, etc. And that's the kind of documentation. And the first step might be to do some kind of color calibration of that, to do that properly and repeatable, etc. But then we can go further and do it spectrally. The image here, by the way, I just was taken just last month at a conservation studio in Germany, where we were kind of experimenting a bit with both conventional RGB photography and some hyperspectral imaging at the same time there. So then there's kind of the documentation, and then another angle is more to say, well, this is a tool for scientific analysis of different, of the objects. Which is very related to the documentation in some sense, but the focus might be a bit different, And here, instead of comparing to RGB photo, you would kind of compare it to other instruments for invasive or non-invasive, scientific analysis of the object, of the materials, etc. And here, the spectral imaging brings an extra possibility, and extra, a very interesting approach. You can also think about, what you can do with the visualization. I think that's also important to. I mean, this is a very rich data, and you can use it. You could think about doing very precise true color visualization, because you have the spectrum, you can generate the resulting color in any conditions, but there are also many other things you can do that you could categorize under visualization. So I feel that these kind of 3 domains kind of cover a little bit the whole field of things we can do. Now, just some examples. This is kind of going back in history, showing that the multispectral imaging for cultural heritage has a quite long history. This, as far as I know, this is one of the first projects doing this. EU project called Vasari came up with a very nice system in the beginning of the 90s. So this is not something that's particularly new, but there has a lot of things that's happened since then. Another EU project here, the Chrysatel project, resulting in the Chrysatel camera. With a slightly different kind of thing. This is a line scanner system, but still a multispectral system with with different optical filters covering the range, as you can see in the bottom here. And then there's kind of the hyperspectral approaches. This is a very nice experience we had together with researchers from or with technology from Norsk Elektrooptikk, NEO high specs camera, that independent but Norwegian, so we kind of like to work with them. We are Norwegians, so here we are, with my colleague in the middle, Sony George, together with researchers from NEO and the conservator from the National Museum in Norway, working with this slightly famous or infamous maybe painting here that we have worked a lot with, the Scream. So so then we can do things that has been mentioned earlier, like pigment mapping. For instance, here is trying to map some different pigments. I'm not going deep. I'm kind of just going quickly through these things. But in addition to trying to map the pigments, there's also other, let's say, image analysis you can do. Having now an image, and hyperspectral image, you can try to analyze different things. And here, we can try to look at this the crack patterns, for instance, in image processing from the hyperspectral image in this case. And then this question of making different maps from the images is from the hyperspectral image is a very it's kind of straightforward in some sense, but it's actually quite difficult to prove it because the ground truth is a bit mushy here. So is this kind of okay? So here is a map, two maps. Are they correct? Are they precise? Of course, the mixtures of the artists are not. They are a bit messy when they work, right? They mix everything all over. So so it's still a challenge to do that, but I think it's a powerful tool. Another case of this where, in the Change project, was a EU project that I was the coordinator for, and we had several PhD students in the project working with imaging for cultural heritage in general and spectral imaging in particular. So Jan here, he was working at the University of Oslo at the Aula. You can see to the upper right, there's a really huge room with enormous paintings on the walls. So, and you don't really notice it when you see here, but if you think about just getting up to the painting on the wall, with scaffolding and stuff like that, with a hyperspectral camera, and trying to get the controlled, we couldn't control the lighting in the room. It was impossible to turn it completely off. So there was a lot of interesting challenges around that. So here the purpose was to kind of document and plan cleaning of these paintings. Other example here, still from the same project, this was Agnese working with us with hyperspectral imaging of stained glass windows. So here you have some samples, so in the lab, now you have to move the light source underneath. So it's no longer the spectral reflectance we're trying to capture the spectral transmittance in this case. Now going on site, in this case in the museum in Switzerland, then it's hard to control the lighting. So how can we get quantifiable hyperspectral image on site like this when we don't control the lighting? That was a very interesting challenge. Other project here, working with, you can see in the image here, you have two cameras from high specs covering different spectral ranges. Unfortunately, the sensor technology, this is for you photonics guys, can't you make a material where you can get the range of sensitivity, broad range of sensitivity in the same material, that would be nice. Now we need 2 cameras to kind of cover the broad range we want to cover. So here we were working with archaeological textile fragments from the Viking Age. We have done a lot of other research on these, also try to also solve the puzzle problem, trying to put them together, trying to understand what's going on there. But the spectral imaging is one of the tools we have been using for that. Manuscripts is another big field. In some sense, working with manuscripts, often one of the main goals is just make it readable, right? And that's a different kind of ground truth, a different kind of research in some sense. Of course, we're also interested here in what inks were used and how are they changing, how are they fading. A lot of things around manuscripts that are very interesting. But sometimes kind of just this kind of making it pop out and making it more readable is a very nice thing to work towards. Again, another type of field here, we built our own system. Again, it was mentioned using LEDs as active illumination. So here we have a system for transparency again, for films, building the LED lighting in the bottom and having kind of the adapted object now optics for that. Using it for many things, but in particular here in the project, we used it for restoration, virtual restoration of a specific old photo technology called autochromes. We talked about snapshot before. This is the spectral filter array approach. Is one very simple and straightforward, way to do a snapshot multispectral image. So it's a straightforward extension of the color filter array that's used for color, and brings a lot of possibilities, a lot of challenges, a lot of things. This is kind of the domain where the spin-off company is working or specializing in. So I should, of course, take the opportunity to talk much more about our spin-off company, but we'll do that another time. So open questions, or we talked about multispectral, hyperspectral. So how many channels do we need, right? That's a big question. And I could spend time going into many different ways to try to answer that question. This one to the right, looking specifically at, pigment unmixing or pigment mapping with hyperspectral versus multispectral. Or what about the whole range of research that tries to actually recover the spectral reflectance from RGB data? AI is very powerful, so do we need a hyperspectral sensor or a spectral sensor if we can recover the spectral reflectance from RGB? Good question. I have more questions than answers to you, by the way. Software we mentioned. This is a PhD project right now that she's focusing really on the visualization and on the software and the platform for that. It's so important to kind of bridge between the very fancy technology we're talking about here and the users who might be conservators, and how, what kind of software do we need in the middle there. Second to last slide, just mentioned a new project starting up using different imaging technologies for culture heritage, still multispectral, hyperspectral, terahertz, ultrasound. We will be recruiting PhD students this fall for that all through Europe. And that's about it. There's already too many things to say, but things to discuss really still, I put some bullet points here. You guys, come with different cameras, right? Which camera is the right camera for a specific culture heritage, use? Well, you will all say that's your camera, of course. Now, what about the user? Do they need to go to the scientist to use this, or is this something that can be used by the photographer or by the conservator? That's an interesting question. Many interesting questions to discuss, both on theory and applications. And I think I overspent my time, so there's almost no time for questions. But anyway, thank you.
Thank you, John. Yeah, 10 minutes was a bit too short, maybe for you.
Yeah, sorry.
Yeah, so maybe you can take one question for John. Of course, if you have other question, you can contact John, afterward anywhere, or contact us, and we'll be pleased to put you in contact. Maybe one question from my side, John. You mentioned it at the end, but about a non-flat
Yes.
object. So what is so I guess it's a huge part also of the work, and what is the last development on it? Is it possible to combine, spectral?
Because in let's say in non-flat is also understanding that objects are not necessarily matte. They might be glossy, and we talked about that earlier as something we can avoid. We can reduce the problem of let's say glossy surfaces by polarized light, but maybe we want to capture it. Maybe we want to, go into appearance. Maybe we want to really capture fully how an object looks, and then you need to go in, to capture from many angles and a lot of things like that. So I think it's ongoing, both from a theoretical and also practical. What do you actually do as a photographer when you have a 3D object and you want to do color management and do things in a calibrated way? How do you do flat fielding when you have a three-dimensional object, right? Or either so. No, I don't have the answer. Sorry, but it's a interesting ongoing topic, I would say.
Yeah, also maybe about the illumination process, how do you illuminate 3D object?
Yes.
Yeah. Okay, so thank you, John. Thank you very much for your nice overview of the topic. And now, we welcome our next speaker, John Giecrist. You are Managing Director at Clyde HSI. So John, welcome, and please, the floor is yours.
Yes, if Nitin could please release his, that would be great.
Yeah, Nitin, can you stop sharing your screen, please?
While we're waiting, let me say I've taken this idea of photonics for cultural heritage quite seriously over many, many years now. We've been active in cultural heritage for almost 20 years, and I want to follow some of the things that the other John has been talking about. But I also want to thank Nitin for something that I didn't realize about the laser cutting and so forth. That's really great. I hope everyone can see the screen well.
Yes.
We care about optical measurements in art, heritage, science, and conservation. I'm going to talk about the differences between these two because I think it's very pertinent to what one might have. Now, the first question is, what are the three R's? It's not reading, writing, and arithmetic. As you might imagine, it's robust, repeatable, reliable optical measurements. That is super important. And the reason for that is that there are a very large range of optical technologies and optical spectroscopy and complementary techniques that are all used for heritage, science, and conservation applications. From straightforward photography all the way through to infrared reflectography, as conventional imaging techniques, and then on the right-hand side, spectral imaging, and that could be multispectral or hyperspectral. We'll talk about the real definition of hyperspectral in a few moments. But those can also have different modalities of measurement, for example, luminescence or Raman or reflection or transmission and so on and so forth. All of this has complementary information from single point spectroscopic measurements. And so I was very interested by John's talk on this because it follows a lot of thought that I've had over many years. And then we come to how do we extract useful information from the data that is recorded, and how do we ensure that those data have the appropriate calibrations for meaningful interpretations. The problem is that there are many application examples to consider, and that means there's a whole range of practical issues to be dealt with. And whatever you do in cultural heritage, there are always more things to take care of, and there are always complementary things to add into the mix, for example, micro XRF. So you might want to do elemental analysis as well as chemical analysis. So the research challenge is one of bridging the gap between high-end spectral imaging heritage science. I talk about science now, rather than practical applications in cultural heritage. So this is a range of, pretty pictures through to crunchy real physics data. And there are lots of interesting things in between that, in which many people just don't know what the real correlations are and so on. For many people, a pretty picture is good enough. Shows the distribution of something, shows something there. On the other side, if you want to look at the real spectroscopy, then you have to have robust instrumentation and robust calibrations, so that you can well understand the results that you are hopefully measuring well. So the research challenges I see in all of this are standardization, calibration, the complexity of the materials that one is looking at. They are never individual pure things. They're always in some way mixed with binding materials or varnish, or they may scatter, and if they're scattering, that will change the spectral positions, it will change the spectral widths. There may need to be some corrections by known scattering parameters. And of course, when you put light on things, they may or may not degrade, so that's also a complexity that has to be taken care of. And then it comes to be the point, how much data is really needed for this task? And how do we deal with the complexity of that data? And it was quite interesting to hear Maria's talk and John's talk on similar things. Nearly every cultural heritage application that we've been dealing with involves multimodalities. So there's reflection imaging spectroscopy, spectral imaging, hyperspectral imaging, multispectral imaging. There's micro XRF for elemental analysis, and we've been very active in the fields of all of this and making interactive solutions that allow data fusing techniques to be used so that we get 1 + 1 = 3. The last thing to consider is how to acquire that spectral image in a robust, repeatable, reliable fashion. And that in itself is an art. And it's an art because there are many complexities involved in illumination, in collecting the data, in the mechanical stabilities of any system that you may have, and so on and so forth. So what we do at Klein, and we're 20 years now in hyperspectral imaging, we make hyperspectral cameras. We manufacture hyperspectral cameras for a range of applications, including police forensics and cultural heritage science applications. Today, we have installed over 650 complete measurement systems. So I think that's not bad for a little company in Glasgow in Scotland. And we do that because we place our value at a reasonable price for customers. Marta introduced push broom hyperspectral imaging. So that was very nice of her to explain that for me. And I want to say that one of the key things that we consider with push broom hyperspectral imaging is its superb ability to have high spatial and spectral resolutions. To measure at very high speed, we can easily do 400 line frames a second. And even at 400 line frames per second, we can have a superb signal to noise ratio. Everything that you measure depends upon signal to noise. If you don't have a sufficiently good signal to noise, you can't do a good measurement. And if you can't do a good measurement, you can't analyze something. You can't analyze the data to get useful, meaningful information out of it. The other thing that's really good about push broom is it is absolutely fantastic for low light applications. We are typically using less than 2000 lux in the visible for hyperspectral scanning. And if you listen to the museum people, that's a very acceptable illumination level. So today we've supplied instruments and scanners for all sorts of applications in cultural heritage. This is just a small selection. I won't go through this. It's just each one has its own complex challenge for illumination and measurement and so on and so forth. It also has challenges associated with the ground referencing, or as John would say, ground truth type data. So that's really important as part of the way of trying to understand what the artists were trying to do at that time. We have scanning systems which are fixed in place. For example, the one on the left is at University College London. The one on the right is the main cultural heritage center in Madrid. And that's a portable scanner which they use in the museums as well as they use in their dark rooms. We make hyperspectral cameras from ultraviolet to shortwave infrared spectral regions. But we are also very pleased to say that we have a collaboration with Neo HiSpecs. And that collaboration allows us to put their fantastic shortwave infrared up to 2.5 micron push broom cameras onto our systems. And today we're collaborating with the very nice people in Oslo, and I'll talk a little bit more about that in a short while. We also do microscopy hyperspectral measurements, and so more or less 1 micron from 400 to 1700 nanometers, multimodal microscope systems, and for transmission, reflection, luminescence, polarization. So it means you can measure birefringence of materials. That's quite important. And if you have a Raman camera, you can add Raman to it. It can scan 30 centimeters by 30 centimeters in 1 hour at 1 micron resolution. It's really fast. The Raman camera is unique to us. This was developed originally at the request of Japanese police, but it's now found very interesting applications in heritage science. So here's an example. Here's La Ghirlandata. It's a Rossetti painting from the Guildhall Museum in London. It's their centerpiece. Bank of America paid for its, and I always get this wrong, Marta can correct me, its restoration or conservation. All my art heritage science people roll their eyes when I get it wrong. But the interesting thing here is that within an hour, we've measured 60 high-resolution scans that we mosaic and simultaneously measure from 400 to 2,500 nanometers with 75 micron spatial resolution. And we take care of the fact that this painting is not flat, in that we have distance control for autofocus that maintains the object spot size on target to be absolutely the same throughout the whole scan. And so you can measure these things really fast at high resolutions. So 75 microns over a painting, which is 1.3 meters by 0.9 meters in an hour. That's what it looks like when you zoom in. That's a true hyperspectral image measured from that system. It's just fantastic. You can see everything to do with the way it's been constructed. And if you add UV illumination, you can do luminescence, so you can look at all sorts of other things like phosphorescence and fluorescence materials on target. And if you're lucky enough to have an X-ray machine, you can add the X-ray images into our software already today. So that means you can do multimodal analysis. And if you have a micro XRF like a Bruker, then you can add that data directly into our system as well. And that means you can directly look at chemical areas of interest and elemental areas of interest. So it's all about trying to extract more information from the data set that one can quickly measure. So this is important because if you start to do this, you can actually then be quantitative. I remember we're interested in robust, repeatable, reliable measurements, and if you can then do classifications and understand the distributions of materials and what those materials are, and so on and so forth. This particular measurement was about 5 minutes, and that won a 400,000 euro order. So we're quite pleased with this measurement for that reason. Everything is connected in some way, and our software is involved in data acquisition, control of the instruments, visualization, analysis. You don't need to go anywhere else if you don't want to. It has method files for the acquisition and for an analysis steps, so you can write a script. It has a very comprehensive range of calibrations, which means the results can be transferable. And most importantly, you can have all the metadata associated with all the measurements. This is important because you may want to process this yourself in some other ways. So you can take the multimodal images, and then you can put those into pyramidal and curtain viewers like this, and you can go, we can store 4 hypercubes in this image and go to multiple wavelengths, multiple spectral regions, XRF data, and so on and so forth, and compare all of these together. So it's very, very powerful for the heritage scientist. Now, making robust measurements is not just about spectral cameras. It is about how to take a system approach to make these things robust. If you don't take that into consideration, you're in trouble, because you can easily do things in a kind of wrong, unstable way. And this is example of a genuine Van Gogh, which was brought to us, and the owner used a 10 euro easel to hold his painting on. He brought 2 Van Goghs. We couldn't understand it, why he had a 10 euro easel. But we measured it, and we were able to see the construction drawings underneath and all sorts of interesting stuff to do with the paints that were used. Quite interesting, the reuse of canvases. So we care about this issue in hyperspectral or optical space about the high dimensionality, and we care a lot about uniformity. That means that every spatial pixel in the hyperspectral image should be considered as a point that is recorded by the same spectrometer. That's not necessarily true for all instruments. There are all sorts of issues associated with spectral spatial correlation errors and so on and so forth. I'm not going to go into lots of detail, but you'll understand the reason for this in a moment. Stability, of course. You sometimes measurements take a while. You have to go and repeat something. You want to be able to correlate one set of measurements from day to day, from one painting to another painting, and so on and so forth. So stability is super important. And then calibration. John talked about illumination. He talked about standards, and we're 100% behind that. That's a very complex problem to do with spectral, spatial, radiometric, as well as the corrections that may or may not have to be used for a spectral camera in order for it to operate correctly. Some manufacturers numerically correct their optical errors and their spectroscopy errors, and we feel that's not the right way. You should get it correct in camera. And the last thing is you obviously need a sufficient signal to noise ratio and a sufficient dynamic range and a sufficiently good noise floor in order to accomplish the task well. And so this is a lot of consideration, because signal to noise ratio has nothing to do with cameras in the end, actually. Cameras are great. It's all to do with your system approach and your illumination and the reflectivity of your targets. I don't mean reference targets. I mean the actual painting or or art itself. And then we come to the problem of moving from 2 dimensions to 3 dimensions. And we do hyperspectral 3-dimensional imaging, and that presents another whole additional raft of problems associated with illumination and correction of illumination and so on and so forth. So coming out,
John,
yeah,
please, I will ask you to finish. I'm sorry.
yes, well, I'm just finishing. So so we're just now at the point of the international standard for hyperspectral cameras for the characterization and testing of these devices, from ultraviolet to shortwave infrared. And we're very pleased that we were able to push this through and have it published in October 25. This was a 7-year project, in fact, with industry specialists, not just spectral camera manufacturers, but also end users and from the academic life as well as industrial lives. So we're very pleased about that. So I want to finish with a test. This is to be or not to be William Shakespeare. That is the question, whether the painting was a result of the folio or the folio is a result of the painting. That's the $200 million question. The painting is on a board which is definitely from 1600, so that's definitely of the era. So what do you think? Not sure? Okay. Here are the 2 hyperspectral images, one in the Vina and one in the infrared. And the Vina one you can see is truly photographic. The infrared one you can see there's been changes in it. And when those changes were made or how they were made is not really known yet, but they are of materials of the period. So that's about what we can say. And if you want to follow this up, I'm going to make a small advertisement now and say, if you go to Netflix, you can find The Stuff of Dreams, and it's now also on PBS America. And if you're flying KLM, you can see it on KLM infotainment system in the plane. And you might notice that there is one kind of hyperspectral crazy guy on the right-hand side bottom there. So there we go. So I want to thank everyone for this, and to say that, you know, cultural photonics for cultural heritage applications is a complex activity, and it all depends what you want to achieve. Do you want real science or do you want a pretty picture? The way you attack that is quite different, and I hope this has been interesting for everyone.
Yeah, it's very interesting, John. Thank you very much for your presentation. So since we are running a bit late, if you want to be in touch with John or ask any question afterward, feel free to contact me, or you can already contact John during the meeting.
I'm sure the other John's going to question me on this.
Yeah, for sure. But I'll let you do it, guys, or you can, send me an email afterward. I will be pleased to do the connection anyway. So thank you again, John.
Okay,
Thank you
it's
so
a
much.
pleasure. It's a pleasure.
And so let's welcome our next speaker, Emilien Leonard from IROX. So Emilien, please, the floor is yours.
Thank you. Thank you very much. Can you hear me?
Yes.
Wonderful. So I will talk about pretty pictures to take Clyde's reference, which is a little bit our it's a little bit more than pretty pictures, hopefully. So my name is Emilien Leonard from IROX, and we are a 3D digital microscope manufacturer. And I will speak specifically of our application for cultural heritage. I will speak quite a lot about the Meisje met de Parel, the girl with the pearl earring, from Johannes Vermeer, which I had the chance to inspect quite a lot in a lot of details. But maybe one step back, and also a little bit of the Scream. And I did have the chance to work with some of the speakers of today on this painting. So Hyrox is the inventor of optical digital microscopy since over 45 years. We are optical manufacturer. And in the field of cultural heritage, our systems are used mostly for 2D and 3D non-destructive inspection and measurements. Quite often people are asking me what is who are the users in these fields, and often they are conservation and also science. So both are, let's say, equally using our system, but also public outreach, which I will show you also in a few minutes, how to share data and how to engage public. Flexibility is, I think, one of our most important strengths in terms of stance, in terms of magnification, illumination, including UV and infrared. And our technology can be used for various objects. Of course, this presentation is quite heavy on paintings, but we also have a lot of users looking at sculptures, at furniture, metal object, paper, textile, jewelry, glass, ceramic, and more. And very often it's used for the measurements of depth or height of material, to be able to zoom up to the pigment level, to visualize and measure cracks, loss of material, and also to create gigapixel imaging. Originally, we sell in aerospace or semiconductor industries in very wide range, but we really started to develop our product in this field by creating custom stands for large objects, basically. So those are some of them. And as I said before, we are optical manufacturer. This is our latest, let's say, lenses, and for each of the lenses we have various adapters, which gives a wide range of illumination technique. With high magnification, we can have a small depth of field, so only a small area or small part of the image is in focus, and we use this small depth of field to create a 3D. So what you see here is a real-time video I captured while inspecting a girl reading a letter at open window from Johannes Vermeer. And you just select the range, and the software very quickly capture multiple images to have one image where everything is in focus, and then you have a 3D representation that lets you measure the depth of a feature. For example, between those 2 points, we have 337 micrometer. We'll maybe just move a little bit. Yeah, we can also display colors, which represents the altitude, which is very useful to understand complex shape. So this is some part of the curtain in the painting, which Vermeer used extra impasto, a little bit of white to create relief. And this is one application, is to measure it. Another typical application is our 360-degree rotational motorized system, which we call the rotary heads, and this enable you to kind of fly above the object, regardless of the size and the shape of the object. And here is an adapter at the end of the lens that is rotating. This is extremely useful to understand complex shape. This is one case here at the National Trust a few months ago, where we looked at a very large pearl, which was mounted with a lot of jewelry around it. Here we used a special illumination, diffused lighting system, and we could get very nice result here. I will continue a little bit on large objects. Here we have a special stance that can be very easily mounted on weird angles, let's say, which lets you go quickly to various difficult to reach area. And I had the chance here to inspect the walls of Notre Dame de Paris, to look here at those marks, which are marques lapidaires, which are kind of signature from the stone cutters of the walls of Notre Dame de Paris. And I could very quickly here implement nearly 3 meter high implement our technology to do 3Ds directly off the walls. So it's not very common to be able to do this on a microscopic level. Of course, every time when I'm mentioning 3D here, I'm talking about less than a millimeter. In this case, we have 960 micron, but we can see up to 1 micron in the depth. And now we have customers that have both, that needs both flexible arm stands, but also kind of flat objects. So we started to develop a lot of custom stands. This is one of them, one that we developed for the British Museum, where they have different departments that are using our system, and the goal was to go quickly from a flat object to a 3-dimensional object, and have a complete solution, keeping the ergonomy of the user in mind, with also keyboards and mouse and screen and so on, so that they are ready to work fast, and also on a portable system that can roll from place to place. So let's go back quickly to the girl with the pearl earring. 2018, I've been asked to do some inspection during the Girl in a Spotlight project. This was open to the public, which is also more and more common. And as our system creates stunning images, it's a very visual approach that the public can understand. Here I was looking at some details using UV light. So this is first a visible light, and then this is here UV 365 nanometer. You can see very well here the retouches that have been applied, and you can see also here the white here gives quite interesting information, being able to see this kind of pigments. And actually, this is what really kickstarted our solution for cultural heritage. And this is the first time that we developed a stand with large motorized axis. So in this case, 50 times 50 centimeter with 200 nanometer steps. And then here we could, for the first time, scan with the microscope, as far as I know, at least on the digital microscope scale, scan an entire painting with about 10 billion pixels. So this was 9,000 multifocus images. And then this is an example here where you can see the eye and a little spot of white here in the eye, and then we are able to measure the height of this. Or here, for example, the pearl, obviously the most famous feature of this painting. And here there is a highlight on the pearl. And this is a 3D stitching. So we combine, I think here about 200 or 300 3Ds together to see this panorama. And then here you can visualize the depth information here. So we have the color image and the topography through our focus stacking. And at the end of the COVID, I proposed to the Mauritshuis to do another scan, because my goal was to do everything in 3D, not only some detail, but I really wanted to have the entire painting. And so we just before the museum opened again, I had the chance to do a new scan at 90 times magnification. The first scan was at 35. This is pretty heavy. It's 88 hours with 41,000 3D with a resolution of 1.3 micron per pixel. And this there I used a polarization filter instead of the side lighting, which I use for the first scan. And you can see a better color reproduction, much better depth information. And this was, I'm just explaining a bit about here focus stacking. This is one multifocus here as an example. We started with the upper left and bottom right to select the area, and then on each of the 41,000 we created here focus stacking. And then at the end, we had all those information, all the images were stacked, all the 3D were acquired within this 88-hour time. And then we could put it together. We developed a special software called the Big Picture to be able here to put everything in a single large file, both in color image and in 3D image, and we made 108 billion pixel in 3D. And this is just a little representation to see how it looks like. To get a feeling of the, let's say, resolution, this is the ultramarine pigments here at 90 times magnification, so you can really see a lot of nice detail. And we put on our website this scan, and you can you can explore it if you like directly from your mobile phone or from your computer, and it is very smooth, so you can simply zoom in to a specific area and be able to see individual pigments. We also added a little 3D viewer, so you can play a bit around if you wish to see here the topography. And you can even operate it from your mobile phone if you like. So I let you explore it in the future if you want to. And this is here if you want to make a screenshot or take your telephone, you can directly go to this panorama. And one of the really interesting features for me was to be able to do, and one of the dream was to create a giant 3D print of this painting. And here, this is now the Mauritshuis in Den Haag, where this painting is located. And at the entrance, at the foyer, you can see here a 4 meter times 3 meter 3D print called elevated printing by Canon, and you can come and touch and feel the painting, which is pretty unique. Plus 4 different areas at 140 times, so even higher magnification. It's I think the first time something like this have ever been made, which is also again a great thing for public outreach, both in terms of scientific approach and possibility to share it with the public. Then following this T-stand, we also had the chance, actually the T-stand originally was developed to be able to inspect here the Nachtwacht, the night watch from Rembrandt at the Rijksmuseum in Amsterdam. And a very interesting way also is to use these T-stands on a workstation on wheels to be able to go directly in the museum, in the gallery. And here, this is another Vermeer had the chance to inspect quite a few called View of Delft. And here I'm using raking lights. And what is quite interesting is that it is inside the gallery with the frame, with glass. So we didn't have, you can see actually at this point here, the reflection in the window. So we didn't have to remove the glass or to remove the frame, which makes it obviously very, very nice to use it in situ. Yes, another very nice application here for paper, which is the Vitruvian Man here, Leonardo da Vinci. And just wanted to show you here the belly button, which is quite interesting. This is paper object here, and you can see it's about 0.5 millimeter. That's the center of the hole of the compass, which was created to, which was used to create this circle, perfect circle. And you can see here very nicely the fiber structures, which you can also measure. And again, for public outreach, there are now screens, touch screens there in the Galleria dell'Accademia in Venezia, where you can zoom in and zoom out, and the public is involved, let's say. Yeah, then we started to create a bit kind of hybrid stands, which have where we have a gantry system, so the lens is above, and the motorized XY stage, XYZ axis are above the object, so we don't move the object, but we move the here the motorized axis. Plus, we can move here a frame back and forth, and those are custom developments that we do for museums based on their existing equipment. So in this case, they already had this table, and we developed here the gantry system above it. And then by going further and further with the gantry system, we developed this one, which is here 1 meter 50 times 1 meter at the Munch Museum in Oslo, which gives possibility to be to have much larger scanning capabilities. In the past, we were fixed with 50 times 50 centimeter. Now we can go up to 1 meter 50 times 1 meter 50, fully motorized. And this was one of our first prototype that we tested here on a small autoportrait from Rembrandt at the Kunsthistorisches Museum in Vienna. And this is one result at 10x with visible light. So this is also the result of a gigapixel. And the same exact scan with UV 365 nanometer and here infrared 940 nanometer with the same equipment. And I was...
Sorry, Emilia, I will ask you
we are close to the end. Okay. Maybe a quick one for our Norwegian friends. This is the first scan of the screen here in 2012. I mean, the first scan I had the chance to do with Hyrox. And it was quite interesting. This is at the National Museum. There was quite a lot of loss of color due to some surface change because there is no varnish on it. And I had the chance to look at another screen here at the Munch Museum on cardboard in 2024 with a T-stand here 1 meter times 1 meter. And it was about 21,000 multifocus. This is overnight check with different webcam. And I had the chance also to create a very nice 3D print here, which gives you the possibility to touch and feel. It's very realistic, so it's very interesting. Now, the rotary head was also used here for looking at the surface of the painting. You can see very nicely here the texture of the cardboard, and here some damage. And here, keep in mind that the lens is rotating, and obviously the object stays still. You can see here some pretty strong damage there. And a final development, which is, I think, one of the first. You are the first to see that, to be able to use a gantry system like this and transform it into T-stands, which I think is the future for our technology. So that's it. Here are some information about the museum, our museum page, and you can contact me. We are in various continents, so if you have any questions in different places, don't hesitate to contact me, and I will forward you to the appropriate persons. Do you have any questions? And first of all, sorry, it was quite dense. Usually it's more than an hour.
Yeah, it's a passionating topics anyway. So we could talk about it for hours. So I will not be able to take some questions because I would like to be fair with our next speaker, the last one. But yeah, anyway, maybe Leonard, you can put your email address in the chat, then people can contact you.
Yes, I'm not sure how to stop the screen sharing though.
Yeah. And yeah, next time I will plan a 3 hours meeting. It will be more suitable
for me or
for everyone. So thank you very much again.
Right.
So welcome our last speaker of the day, Ali Kamalabadi from Spectral Tech. And Ali, please, you can start your presentation.
Hello everyone. Do you see my presentation?
Yes, you can start, Ali.
Perfect. So I'm Ali Sadi Kamalabadi, the CEO at Spectral Tech. I'm going to explain a little bit about the company first. Okay, so Spectral Tech is a company which works on spectral imaging solutions, specifically in the area of cultural heritage and agriculture. We are located in Portugal. Spectral Tech has a wide range of products where we have clients in different continents from Europe to Asia, South America, and North Africa. I've been in Spectral Tech for about 7 years. I manage the day-to-day work of the company, mainly related to production and the relationship between the clients and the company, and also the partners with the company. So I'm going to talk about the art conservation area and what needs triggered us to make our solution. So there has been a need for the art conservation scientists, art historians, and collectors for a solution to analyze their work, which could be a paint, drawing, and essentially any object that could be photographed in their work. So our solution focused on the following six main needs of them, which are documenting the information of the art conservation work, which could be, for example, a paint. Then how would be a surface condition, for example, if it is damaged or if it is fixed, or if it is any intervention in the work, and etc. And next, what are the materials and pigments have been used in the surface, and where are they located, where are the materials are located. Also, visualization of the work is in it. For example, they want to see how does a sample or an object looks like in different spectrums with different layouts. How does it look like at UV range, at visible shortened range, and also could be in near infrared range. And finally, they want to have a full report of the related work with all the information included. So we found the XPCAM solution as the answer for the six main needs of the people who were working in this area. Initially, XPCAM started and developed as a European project, and it turned to a real product for the market of cultural heritage. XPCAM is a workspace that is based on spectral imaging with advanced automation mechanisms and processes with the cloud technology infrastructure, which answer the needs of cultural heritage scientists, collectors, tasks, and problems. So this solution consists of three main products, which are XPCAM XO2, the main multispectral imaging system, which is a C-mount camera with 30 different filters from 350 nanometers and at UV up to 1200 nanometer of near infrared. This camera is equipped with a 6.5 megapixel sensor with the color depth of 8 bits and has an autofocus mechanism which aids acquiring fast images for this range of the filters. XO2 runs by a software called XPCAI, which could be installed on a PC, and it only is powered up with the USB cable connected to the computer. It means that you can take the camera to wherever you want in the museum or in a place that you want and do the acquisitions. Since this camera has a C-mount for the objective lens, it could be integrated and coupled in microscopic systems, Raman spectroscopy, and any area that multispectral imaging could be applied. You can see the camera in the slide, and then we have our lampa, which is our power portable plugged-in light source, which covers all sensitivity range of XPCAM XO2 in one device, which works wirelessly with the camera. It has UV, visible, and near infrared light sources. And finally, we have our XPCAM Cloud, where all processing, analytics, AI reporting, and sharing are performed. So this is a research article published in the past with the XPCAM solution on stamps, which is a stamp but made in different places and in different times. So we have 4 different stamps of the same model. In the following analysis, we saw that the first one was not identical to the others. You have the link to the published paper in the slide, then you can have you can read it. In the same platform, we can visualize Cortin and play with different spectral bands like UV, visible, or near infrared, since the light penetrates differently in different spectrums, we can see what is on top of the object, which is here is a stamp, or what is underneath of the top layers. So the images of the above row show the underlying UV layout, which is an image of the top surface of the stamp, and the images of the below row show the underlying near infrared images, which are in more depths of the stamp. Also, in the platform, pigment analysis, characterization, and mapping are performed automatically with our AI solution, which is implemented in our platform. As you can see, the pigments are shown with their related percentages in the table at the left side in the slide. All the results and works are in the platform, and they could be shared with many users in the same group or outside of the group to work on. Finally, all the results are assembled again automatically in an organized report for the end user to edit, work on, and finally print. Yeah, thank you very much, everyone, to listen. If you have any questions, I'm here to answer.
Thank you, Ali. Yes, if you have question, you can raise your hand right now. And same, Ali, if you want to add your your email in the chat, and people can ask question by email, it will be maybe easier because we are running out of time. So I would like to finish this online technology meeting, and thanks all of our speakers today. I hope that you enjoyed talking about these topics. I really enjoyed, to be honest. I'm not an expert of this field of application, but it's very interesting, and I think we will organize more in the near future, because a lot of things still remain in terms of challenge. So thanks again for all the talks, all the speakers, for all the participants and question. And yes, see you in another EPIC meeting, and we stay in touch. Thank you very much.
Thank you.
Goodbye.
Bye.
Thank you very much.
Thank you.
Bye.
Thank you. Bye-bye. Bye-bye.
Goodbye. Thanks a lot.